Hi all. I'm going to go over these questions that you left me from the exit ticket. I tried to kind of categorize them and I will attempt to go in order. So the first one is, why does the ionization energy on the x-axis decrease as it goes to the right? So, such as number 2, does the order of the ionization energies on the graph correspond to the order that we write our electron configurations? Yes, as long as, if you look at number 3, which order do we draw the peaks? Is the x-axis decreasing or increasing? Be careful because it can be both. All right, so you always have to look at your PES graph or PES spectrum, they're called, before you kind of commit to. And then number 4, confused about the relationship between ionization energy and energy level values, energy level energies. Okay, that's a good question. So ionization energies are always going to be positive because it's how much energy you need to put in to removing an electron. Energy level values are always negative. Okay, we learned that earlier. So they will be equal for a particular electron. These will be equal in magnitude but opposite in sign. If you look at this next slide, and you imagine that this is 0 energy, meaning that the electron is infinitely far from the nucleus. So remember, if you think of this as the nucleus and like these as the individual energy levels, okay, when an electron is completely removed from the nucleus, it's going to have 0 energy. Therefore, it would take 0 energy to remove it. That's the answer to that. So think of the origin as the nucleus. And a lot of times that's how these graphs will be set up. But stay tuned for answers to subsequent questions. As you have it done like I just showed you. So this would be like your 1s. This would be your 2s. This would be your 2p. Okay? Saying this is definitely the nucleus, because if this is a low value here, then you would say, okay, your nucleus is over here. So there's not one consistent way of showing it, though I would say more times than not I see it like this with a decreasing value for the x-axis. So relative number of electrons means it's not absolute. So notice on here there aren't actual numerical values, but we can look at this peak height and then we can compare it to this peak height, which looks like it's more than double the size. Okay, so you could take like a ruler to measure peak heights. Sometimes you will have little like tick marks here. There won't necessarily be values, but it'll be very easy to see, oh, okay, this is, 2.5 times the height of this peak. Now, couple the relative heights with what you know about how many electrons can fit in each sublevel, and you'll recognize, oh, okay, if this is a 2s, you can get 2 electrons here, and then if this is a 2p, you could get a total of 6. If it's not quite 3 times as high as this one, then it wouldn't be 6, it would be 5. If it's twice, it would be 2p4. But again, a lot of times you'll have tick marks here that will help you with that. On who published the graph, sometimes these peaks will just be lines and you won't even like see areas under the graph, in which case then you definitely go by the relative height, but typically you go by the relative height. Don't stress about the areas. We're not having you integrate areas below curves in this class, so just look at height. So this set of questions is talking about the y-axis. So the first question in the graph, the y-axis is labeled relative number of electrons. What is meant by that? This question is just saying, are the relative areas that like proportional to the relative heights? You'll see it very differently depending. And then how do we figure out how tall the peaks are relative to one another? So again, it's going to be a lot easier if you have like tick marks here. They're not going to have numbers on them, but you'll at least be able to gauge this peak versus this peak. You can see that this is 1/2 the size of this one. And if this is your 1s, this is your 2s. Oh, okay. You can write an electron configuration 1s2, 2s1. All right, I'll go a little out of order here. We'll start with number 8. This is an important question, which is why I started. What's the difference between potential and ionization energy? And why does higher potential energy correspond with higher energy levels? So this is basically something we've learned previously. So potential energy is going to be negative. That's the energy of the electron. So the potential energy is going to be negative, and the ionization energy is always going to be positive. So this kind of relates back to a previous question that I answered. And why does higher potential energy? So it's actually why does a less negative potential energy correspond with higher energy levels? And that's because here's your nucleus, and then you have energy levels that are further away. You have energies of electrons becoming less negative as they reach infinitely far from the nucleus, or zero energy. Number 9, just wanted clarity on why electrons eject energy. So if an electron takes in a certain amount of energy, it releases unnecessary energy. What is the purpose of this? So remember, there's something called the law of conservation of energy. That's the, what is that? The second law of, the first law of thermodynamics, law of conservation of energy. So if an electron is removed from an atom and there's excess energy there, it can't just disappear, okay? It's going to be converted into kinetic energy, and it's going to make that electron get removed faster. So number 10 says, do increased frequencies in photons mean higher kinetic energy? I can't say exactly yes or no to that, but certainly if there's leftover energy from the removal of the electron, then yes, it would correspond to higher kinetic energy. Number 11, how were the velocities of the electrons measured? This is actually, you know this from your photoelectric effect gizmo. So if you remember, there was an electric field. So an electron would be, in that case, we say ejected. Here we don't really say ejected, we say more removed. But in the photoelectric effect, the electrons were ejected from a metal surface, and then they came back through an electric field that could be controlled. So you could figure out like kind of the perfect value of that electric field to get an electron to reach like the second plate, and that's how you figure out the kinetic energies, or the velocities, I should say. So is that something you need to like know and would be asked on a test? Not in chemistry, maybe in physics, but not in chemistry. But still good to know. And you did learn about it before in photoelectric effect. Number 12, why does the electron have kinetic energy when it has virtually no mass? Because it's virtually no mass. Electron totally has mass, all right? It's just really, really, really small. Let's go to number 13. I'm actually a little confused on the question. So it asks about the relative amount of electrons a certain energy can remove. One of the principles of PES is that you're only ever removing one electron at a time. Okay, so one electron per atom gets removed. It may not be a valence electron, it may be a core electron, okay, in various inner energy levels or sublevels, but only one electron per atom is removed, and then those resulting +1 ions are kind of taken out of the game, so they can't get hit again. And then how many electrons can be removed from one atom? Again, it's one electron per atom, but how many electrons can be removed from multiple atoms of the same element would be however many electrons that particular element has. So if I didn't clear that up and that's your question, just make sure you ask it in class, please. Now let's go to 14, and this is a really important one. I'm a little confused on how isoelectric atoms may be distinguished between one another on graphs regarding PES. Okay, so first of all, there's a misconception here. You can't have isoelectric atoms that are different from one another. It's isoelectronic, we usually say, species. So that would be, things with like 18 electrons. So that could either be argon, or it could be potassium with a +1, or it could be chlorine with a -1 charge. Those would all be isoelectronic with one another, okay? But you're not going to have isoelectronic atoms. Like you can't have an argon and a potassium atom being isoelectronic. So this is a great question though. How are they distinguished on graphs? So we're going to talk more about this. You're going to do an activity with this, but I will say, I'll give you a hint for the upcoming activity. The difference between these three species is the number of protons. So there are 19 protons in potassium, there are 18 in argon, there are 17 in chlorine. So again, it's just a hint, but this is how they're going to differ based on the nuclear charge, and then you have to think about the attraction for those 18 electrons to those different nuclear charges. The last one we'll talk about is number 15. How do you identify an element based on its PES spectrum? Well, write the electron configuration. All right, and once you have the electron configuration, then you can figure out which element it is.